I'm David. I'm a developer advocate engineer at Argilla. And the function of developer advocate and engineer is actually a function mix between developer advocacy, like into the communicating with the community, and doing machine learning engineering. So like the findings that you get from the community and from our open source contributors are directly integrated within the package by me. Today I will be talking about shortcuts for bootstrapping NLP pipelines, and I will be tackling this from a more of a NLP engineer standpoint than from a healthcare NLP engineer standpoint. But I assume that the shortcuts that I'll be discussing can also be applied to any arbitrary domain, and therefore also the healthcare domain. So the agenda for today is briefly introduce Argilla, because a lot of the analyses I'll be doing are done using the Argilla ecosystem. I'll define a benchmark for shortcuts, do some data exploration using MTSamples dataset. The cool shortcuts that I'll be covering are like weak supervision, few-shot learning, and active learning. And eventually I'll wrap up with some cross-lingual representations that you might be able to use when working with low resource languages. And I will touch upon some of the packages I've created during my work at my previous employer. So Argilla is a open source labeling platform for data-centric NLP, and we really focus on having high quality training data instead of like having a lot of training data with lesser quality, because we assume that if you have like high quality data, that you can start with a decent baseline models and then improve models and robustness over time. On top of that, we also want to enable the collaboration between data teams and domain experts. So the data engineer and the ML engineer, along with the human experts and the data scientists as well. Argilla consists of three components. On the left-hand side, you can actually see the Argilla Python client, which can be used to actually infer information from models, load data sources, create and update data sets, and actually listen to changes in the data sets, for example, to do active learning, to do evaluation, or automatically start model training. And these are also some of the things that I'll be covering within the cool shortcuts that I'll introduce later on. Eventually, the data that you've created actually ends up within the Argilla server, which is in a fast API, REST API. And that actually handles storing and managing the data sets, computes some data sets metrics on record level, and actually stores them within Elasticsearch, where they are like nicely indexed. And meaning that we actually use Elasticsearch as a backend allows for the Argilla UI to actually freely move around within the data, like defining queries, doing filters on metadata and these kind of things. So this means that the annotators working with the data will be way more involved with the data than instead showing these individual records, what a lot of other labeling platforms are doing. And on top of that, as a small bonus, is that you can quite easily deploy Kibana to build like dashboards and these kind of things on top of the data that's within Elasticsearch. So Argilla has some nice user and workspace separation, where users can be assigned to user workspaces or team workspaces, along with some information, API keys, etc. And this is what a dataset overview might look like. So on the left-hand side, you've got the dataset names, the workspaces, in this case, a workspace assigned to David, and the tasks that the dataset is actually covering, and some additional metadata information like created at, updated at, and these kind of things. So the Argilla workflow that we normally start with is the training workflow, where you will have your data source, you are reading your data set to create Argilla records, and these records might benefit from some like inference from models, or like some pre-annotations or initial predictions that you log along with the records into like Elasticsearch via the Argilla server. And then within the UI, you can actually see an overview of what a token classification task might look like during exploration and labeling for an annotator. Eventually, after labeling the data, you'll end up loading your records, and we have some nice methods to actually directly prepare these records or like these training samples for training using, for example, SparkNLP, but also we have integrations with Spacey and with like the transformers library, where you then like train using that library and eventually come up with an initial model. So eventually, when you've got a model, we expect that you continue like monitoring your model requests that come in during your inference pipeline. So what happens is that before actually returning the predictions, you actually log the predictions into Argilla as well, asynchronously, or via the ASCII middleware, where the records will once again show up within Argilla. Metrics will be computed after having corrected for the annotations, and then you also get like direct model performance or model performance for different versions of your models, where you can eventually once again load the records and prepare for training. And this is also how you kind of close that MLOps workflow, where you continuously gather data and continuously are able to annotate data and train models on top of that. So these are some like Python client methods that are being used in the background, but it's good to have some familiarity with the API that Argilla uses, where here there are two examples of token classification records with sole predictions or with a prediction and an annotation. And as you can see, the highest score is actually used for evaluating these metrics. So in this case, the highest score for prediction aligns with the annotation. So then the prediction is seen as a correct prediction within Argilla. After having created records, you can actually log them using Argilla log and a corresponding database. And what you can do is also quite easily load all of these records and then prepare for training. And for example, for the transformers library, that might look like this, where you also have an overview of the features, like the class labels, where in this case, we only have the class label for span. So shortcuts for me are like shorter, quicker ways, methods and procedures that you can use to reduce time and energy to accomplish something. In this case, it would be setting up a NLP pipeline and setting up a NLP pipeline for getting a good enough baseline, and then iterate from there once you have like your more advanced machine learning model in production that was trained on a lot more data. So data exploration. For the use case and toy examples, I will be using the MTSamples dataset, which is hosted on medicaltranscriptionsamples.com and was originally introduced for a Kaggle challenge. And I actually ported that dataset to the Hugging Face datasets hub. So for the analysis, I'll be using the columns containing transcriptions and the keywords, and I'll be focusing on a token classification task for entity recognition. So as you can see on the bottom of the screen, this is actually a way to load data from the datasets from the Hugging Face Hub using the datasets library directly into Argilla, which are like 3 lines of code. If you ever want to play around with a dataset, it's really easy to directly upload it in Argilla, annotate data, and also use the shortcuts that I'll be introducing later on. So this is kind of what data looks like and what the keywords look like, where you have the transcription over here and the keywords underneath. And what I did is for the toy example is kind of go over these transcriptions and come up with some intuitive labels that made sense to me to focus on for the analysis, which are like a medical action that might have been taken, body corresponding to body parts, disease corresponding to diseases, equipments, medication, procedures, where the difference between a procedure and an action is like the entire treatment being a procedure and the action, like, for example, making an incision or these kind of things. The symptoms that people might have and vital signs. Once again, I'm not a medical expert, but I try to approach this from a more NLP engineer experienced NLP engineer view. So within Argilla, what we can do within our basic UI, as I introduced, is actually do text queries that correspond to the Lucene query language, which is native to Elasticsearch, where you can do like these default operators for querying, like, for example, bladder and urethra, where you end up with all the records that match bladder and urethra, or do tumor or cancer And you can also use like wildcard operators like search and wildcard star, regex, some metadata filters, and then metadata filters like, for example, the time or the last updated or the actual model that made the prediction. So you can also differentiate between, for example, different model versions that you might have had running throughout the period of your analyses. Additionally, I will be using a word-to-vec model to go from a supervised approach, because a word-to-vec model can actually be trained without any labeled data, to a semi-supervised approach where you kind of use some examples to generalize your models and assumptions, which also aligns with like the few short learning shortcuts I'll be showing. And then eventually you go to a completely supervised approach where you have your annotated training data, which is correct, and actually train a model based on that. And this word-to-vec model was trained on PubMed, and it's available on bio.nlplab.org, where you can do things like get the most similar like words based on an input word, check whether a word is more similar to one word or another, like stomach being more similar to bladder or brain, and also generate vectors based on that. And I opted for using this due to the fact that you can use these features like most similar to actually expand your knowledge on, but I'll get back to that later. So a nice thing, what was actually introduced in Elasticsearch version 8 is that you can add vectors to your documents, which we also introduced within the Argilla Python client, where you can add up until 5 vectors to each one of your records. So instead of searching directly via queries, what you can do is also query based on like these semantic representations of your vectors, getting the most similar records that that you might want to focus on when labeling data, to really get more sense out of your data. And I was actually inspired by the sense-to-vec algorithm to, instead of adding sentence level vector representations or sentence level similarity metrics, to focus on part of speech tag level metrics. So really focus on the token level, which in my opinion makes a lot more sense when actually labeling data for a token classification task. For example, in this case, you would see these numbers, and querying for these numbers would also result in other numbers that might be used for like indicating medication or the uses of equipment, instead of focusing on the sentence as a whole, talking about liposuction and all other things that might be less relevant if you just want to focus like things about medication. And this is a brief demo of what this might look like within the Argilla UI. So what we actually did is share an entire query URL so that you can actually also share like the findings that you might have with some other annotators or with your manager. And due to the fact that the data is indexed, what you can do is also directly query from within the UI, and which is quite fast. You can do like these wildcard queries, you can do regex, you can like sort, for example, on last updated. And of course, as a nice thing, what you can also do is take a look at, for example, the semantic words that you might want to consider, in this case, anterior, adamacious, and difficult, and really dig down on those words or token levels that you might want to focus on. Then you actually need to remove the query. And then you'll end up like with the 50 most relevant records given these tokens that you wanted to focus on. So the first shortcut I'm gonna talk to you about is weak supervision, where you end up with a raw data set, define a lot of rules and heuristics to come up with a weak labeling model that you can then use as an initial train data set for actually training a default machine learning model. So weak supervision for like healthcare NLP might look like something shown here, where you initially have a subset of lexical rules. For example, if you word the word Foley and catheter next to each other, you can always assign the label equipment, where you have to rule tumor or cancer, like these, either one of these words assign the label disease. Once again, if you have like a wildcard query that matches the word search with any other ending, you maybe want to assign the label operation. Additionally, what you might want to have is a knowledge base, for example, a list of medications or chemical compounds or like whatever, and some from regex queries, where you go from like a clinical data set without any labels to a rule-based NLP system based on knowledge base and some expert knowledge, and actually use that clinical data with weak labels to train a full-blown machine learning algorithm, which you can then use within like the workflow I mentioned before, where you have a model and then continuously improve on that model by annotating data, retraining the model, and introducing a new version. So the nice thing that I came up with was actually doing this weak supervision with semantic rules, where you might have some annotated data, and you might create a knowledge-based word index thingy, where you have a word and the assigned label to it, and actually based on these exemplars, do annotations if the similarity threshold aligns with any token of an unseen record. So in this case, you would have like the catheter was removed. You loop through the text and the tokens and do a very simple, through a very simple heuristic that doesn't require any compute, doesn't and require much time to actually infer the knowledge from, actually assign a label due to the fact that Tankov is a form of a catheter. This is actually a way to quite easily introduce or expand your already known data with some additional labels. And actually, if you go on with this reasoning, you'll end up with few-shot learning, where you might have like a group of words that are representative for a label. And I actually created like this package for that, concise-concepts. It's available on GitHub, so you can search for it. And this package actually creates subgroups of the labels and actually expands over these groups to create n most similar groups based on either spacey or Jensen factors. And this is really built once again on top of the fact that you can do the most similar search using a word-to-vec model, which is very intuitive approach and not compute heavy, where in this example I actually went from 30 inputs words to 50K matching patterns that you might be able to use, where down below you once again see like the text with some terminologies that you might want to pick up on. And none of these terminologies are actually present within the training data, but they are being picked up by the model, which is a nice thing to be able to expand quite easily from your like default knowledge base and rules and some things that you intuitively can make assumptions on for the data set to a lot more conceptual meaning without requiring a lot of compute. And the nice thing is that like the most similar words that correspond the best to a group as a whole, like for example, diabetes, pneumonia, and influenza, the most similar words for the group as a whole do not fully overlap with the most similar words of individual words within the group, as you can see. So what you can actually do is combine this approach of concise concepts with the semantic rules and go from 30 words to 15K words or some more or so less to semantic 15K words, where you can once again match on similarity. And based on that, you can already have like an initial data set with any labeled data and end up with some like decent baseline with already quite some labels based on just some input words and some of the assumptions that you make based on part of speech tags, for example, including compound words and these kind of things, where post-operative pain is recognized due to the fact that pain is a symptom, but post-operative is actually a compound within that word. So if you actually continue with this, you'll actually start defining an active learning loop, because you kind of look, for example, at your data within the concise concepts few shot learning loop. You'll maybe add some words, subtract some words, and then what happens is that as an oracle or annotator and as a learner or like machine learning algorithm or heuristic, you actually start working side by side in order to like label data. And the nice thing is that like these updates from the learner are happening side by side, so they are directly represented in the difficulty of the labeling test for the annotator or the oracle. Where the oracle labels data, this data is actually used to update the model or the assumptions or heuristics you make. This is then evaluated as initial predictions on unlabeled data, and then based on, for example, the last updated records or the most certain predictions, the oracle can then like prefer what to label. So you can focus on the maybe the more certain predictions or the less updated records, and that really helps to kind of go through all of the annotations within a data set. And this is also a thing that I've played around with for creating like plugins or background processes that actually allow us to work smarter and listen to newly annotated examples, update the heuristic model or assumptions, and then copy the annotations based on that or update the predictions. And I've actually made two versions of this plugin where I have a token copycat that directly copies the validated annotations to all of the records within your dataset while you're labeling data. So you don't have to do duplicate annotations under the assumption that, for example, once I've labeled catheter as an equipment, then I would like to see that represented in each one of the records. And similarly, there's the possibility to do this using semantic search, where once again we introduce a overlap threshold between the annotated words and maybe the samples that are within the dataset. And I can actually give a brief demo about this, where like we have our models that we use for the similarity search and part of speech tagging, and we'll actually start listening to the weak supervision dataset while copying annotations and not copying predictions. And what it will do is like create a query the database, and then check if it can copy some of the assumptions that we've here with the annotated labels to other records within the dataset. So what we can do is open this example. Apparently, at the moment, there are no records to update because it has already updated all of the annotations. But for example, if we would go and query for the word tumor, then assign the label of disease, coagulation might be a symptom, then actually validate this record. So we know that the plugin in the background is allowed to use it. Then the plugin will like pick up on these words as being relevant to consider as ways to annotate additional data. Wait a little while, and then eventually 400 records out of the like records that you were supposed to label have been updated. And then sorting here, for example, based on the last updated timestamp will then show us that a lot of these assumptions we made by actually evaluating have been updated as well. So tumor, and maybe we'll also like have better tumor as a disease. So we actually corrected a mistake, wrong annotations. Anesthesia as medicine have also been detected. So this is a really nice way and a smart way to actually avoid having to label duplicate data. And eventually what you end up with is a way to really go from an annotated data set, which is maybe less relevant for the English language, but for Dutch or German or any other language out there, which is less resourceful, to a like initially fairly well annotated data, or at least a data set that has a lot of ways to more easily annotate it. And when you have that, you can actually train a model. So what we have is the way to actually load the dataset, only take the validated or annotated examples, then convert that dataset to a data frame, which then can directly be used within SparkNLP to create a Spark data frame and start a training loop, given that it's KNL formatted. Then as a wrap up, I want to give some references to like one of the packages I created, which uses a cross-lingual model to actually make generalization on a data set for other languages as well. So at my previous company, we're working with private intelligence, and we were really focused on creating like knowledge graphs. So therefore, the coreference analysis is very useful, but there's no Dutch data. And also when you are annotating coreferences, the disambiguities might arise between a lot of annotators. Some people want to annotate longer fragments of text, and some people want to annotate shorter fragments of text. So I opted for choosing this approach to take a cross-lingual model, use the onto nodes existing English data sets, which is used for all of the benchmarks, and actually train based on that. And it generalizes really well for like English, German, and all like other languages that look like Dutch, and also performs okay for Roman Latin languages. But yeah, Spanish, French, and Italian are slightly worse. But still, it's the first like multilingual coreference model, so that's a pretty cool achievement. And I created a classification package, which actually can be used for few-shot learning. It's less robust than, for example, setfit, but it will like create a support vector classifier in the background, heavily overfit on the data, and then can easily be used, for example, during a active learning loop, where you have to wait several seconds to run inference using this model and update the training using newly annotated examples. So that's where it like fits in perfectly without the need of like having a GPU on standby to actually update training steps within like a decent transformer model. So it's less robust, but it's way quicker and lighter and very pragmatic. Then eventually we've got some like sources. Argilla, which is available on GitHub. You can quite easily deploy Argilla with the click of a button to Hugging Face. My LinkedIn can be found there. My packages that I reference along with concise-concepts, coreference package, and classification. And one more package that uses Onyx representations of sentence transformers to like speed up inference and dial down the memory usage. And I do some volunteering. So if you find it interesting, please feel free to have a look. And there are some other packages that might be interesting for people for like setfit for few-shot learning, SK-weak for weak supervision workflows, and small text for active learning as well. And then eventually there's some room for feedback and questions.